Okay, so this is a practice with, again, just the rolling projectiles part before we get into our launched projectiles today. Make sure you have your equation sheet out with your projectiles equations on it. Okay. All right. So this piece of information here that tells us he dives out horizontally, what does that tell us about our 4 meters per second? What variable does that tell us? Good. Initial horizontal velocity, VAX or VXI, either way. Okay, 4 meters per second. What other variable does that automatically tell us? Good, good. Initial vertical velocity, and that's equal to 0. Very good. Okay, it dives out horizontally. Okay, we also know time is 2.2. We're solving for how high was the cliff, so what variable does that tell us we have to solve for? Y final. Y final. Okay, we want to find out how far below where we started, and then how far from the base of the cliff does it land? That's this distance right here. Good, so X final. Okay? We can solve for these in either order because they're not dependent upon one another. Okay, so it doesn't matter which you solve first. You can solve either way because they don't depend on each other. Okay? What other variables do we know that we haven't written down yet? Okay, we know acceleration in the y direction is negative 9.8. And what else do we know? Yeah, Nate? Okay. Our final horizontal velocity is also 4. What do we know about our initial positions? Yeah, both 0. So x sub I equals 0 and y sub I equals 0. Okay, good. So let's go ahead and solve for y final. What equation could we use to solve for y final? The second one. Yep, good. Okay, so y final is 0 plus 0. 1/2 negative 9.8 times 2.2 squared. Remember again, only your time variable is one that's squared. All right, so our y final value, I got something around negative 23.7. Do we agree? Okay, why is it negative? It's landing below where it started. Okay, so if we want to truly answer the question that was asked, and it says how high was the cliff, we would turn that around to a positive value. Okay, because this is telling us we're landing 23.72 meters below where we started. But in order to fully answer our question, our cliff was really 23.72 meters high. Okay? Does that make sense how we made that positive? Okay. And then to solve for x final, we'll take VXI times time. So 4 times 2.2, and we get 8.8 meters. Okay, so on our final diagram here, we can see we land 8.8 meters away, and our cliff was 23.72 meters tall. All right, how do we feel about those? Pretty good? Okay, good. Let's go ahead and move on to our launched projectiles now. Okay, so we're going to start looking at projectiles in which we launch at an angle. Okay, these are things that leave with both a horizontal initial velocity and a vertical initial velocity. Okay, so now they have both. The ones we've looked at so far have only had a horizontal initial velocity. These have both horizontal and vertical. Okay. So a launched projectile is what we looked at kind of right at the beginning of basically an ideal projectile. We launch something into the air. It follows that path, goes up and comes back down in a pretty symmetrical way. Okay? This is kind of an ideal projectile, something that starts and ends at the same height, something that follows a symmetrical path up and then back down. Okay? So that's kind of what a launch projectile is. Now it's starting with both a horizontal initial velocity and a vertical initial velocity. We've got components now of our initial velocity vector. Okay, and we're going to start breaking down that vector into its vertical and its horizontal components. Okay. So let's say that I punt a football with 40-degree angle at an initial velocity of 4.2 meters per second. What are the components of my initial velocity vector? Okay, so go ahead and get your problem written down, and I'm going to kind of draw the diagram of what we're looking at here. All right, so this on the right, the picture on the right is kind of the big picture of what's happening here. We've got an object that's been punted, so it's going to travel both horizontally and vertically to its peak height and return to the ground. Okay, what this is this our initial velocity vector, so it's kind of a zoomed in section of this very, very starting point. Okay, right when it leaves this guy's foot, we're going to zoom in just this little section right here to take a look at that initial velocity vector a little bit closer. Okay, so here is our initial velocity vector that we need to break into its components. Okay, so this is traveling 4.2 meters per second at a 40-degree angle. Okay, and if this 4.2 is our initial velocity vector, what would I call this side? If this is v sub I, what would I call this? Yeah, initial velocity in the vertical direction. And this side I would call initial velocity in the x direction, okay, or v sub yi and v sub yx. Again, it doesn't matter the order you put these two subscripts in. Okay, it doesn't make a difference. So, after I break down this vector into components, that is what I'm going to use for my projectile equations now, v sub xi and v sub yi. Okay, so let's go ahead and solve for those. V sub xi, I'm going to take my hypotenuse times sine or cosine. For x, I'm going to use cosine. Good. Cosine of 40. Make sure your calculator's in degrees. And for y, I'm going to use sine, so 4.2 times sine of 40. Okay, and both of those components have units of meters per second because they're both velocity components. Okay, here's a really important step now. So I've broken down that initial velocity vector into its x and its y components. Now I am completely done with that 4.2. Okay, and the 40 degrees. I will never plug that into an equation. Okay, once I break that vector into its components, I'm using solely those components now. Okay, I'm using only the 3.22 or the 2.7. I'm not using that 4.2 meters per second at all anymore. Does that make sense? Okay, because this is at an angle, and we don't work with things at angles. We work with either horizontal or either vertical. Okay, so now 2.7 and 3.22 would be the values that can go into our projectile equations now as v sub xi or v sub yi. Make sense? Okay, so that's the only change in rolling projectiles and launch projectiles, is that we start with this vector at an angle, we break it into its components, and then we can start solving using the same exact set of equations. Okay, so let's go ahead and try one here. Okay, football is kicked at an angle of 37 degrees to the horizontal with a velocity of 20 meters per second. Calculate maximum height and time of travel. Okay, so you can abbreviate this problem down. You don't have to write it down word for word, right? Abbreviate what you're writing, and then we'll start looking at our problem. First thing that we do, we break down that velocity vector into its components. Okay, so go ahead.
It says, it's saying that angle is to the horizontal.
Exactly. Yep. So it's telling us that our angle is 37 degrees from the horizontal, so it fits right in there. Okay, and where's the 20 meters per second go on? Good. Our hypotenuse. Okay, so let's solve for v sub xi, which is this side of our triangle, and this is v sub yi. X, we're going to take our hypotenuse times cosine of 37. And I get 16. Okay, we can go ahead and round that to a whole number if you want, because both of these are really close to a whole number. And for v sub yi, I get about 12 meters per second. Okay, by using sine. 20 times sine of 37. All right, do we agree with our components there? Okay, so we've got v sub xi equal to 16, v sub yi equal to 12. We're done with that 20 meters per second. Okay, that's not going to go into our problem anywhere. Okay, so if you need to cross that out once you break it down to kind of remind yourself not to plug that in, that might be a good idea. All right, we want to calculate the maximum height or the peak height. What variable does that mean we're solving for? Y final, okay? And if we look at our projectile here, it's going to go up and come back down, okay? We're assuming that the ball is being kicked from the ground level and it's going to land on the ground level because it doesn't tell us it's kicked from a certain height. Okay, so that means peak height's going to be exactly in the middle. This is a perfectly symmetric projectile. Okay, so this is going to help us solve things a little bit easier. There's a little shortcut we can take, and I'll show you how we do that here in just a second. Okay, but what this means is that the first half of our motion should be identical to the second half of our motion. It's going to take just as long. It's going to travel at the same speeds. Everything on the first half to its peak height should be the same as the second half on the way back down. Does that make sense? Okay. So we're solving for y final at this point. Okay, so we want to look at this projectile up to the peak height. Okay. What do we know about an object's vertical velocity at peak height? It's 0. Good. So here we're thinking at peak height, our v sub yf is equal to 0. That's going to help us solve for our final height, okay, or our y final. Do we have an equation that we could use now to solve for that? We could use the last one, right? The third one? Could we use the first one? We don't have time, so we can't use the first one unless we want to solve for time, okay, which we could. But we can use the last one, right? So v sub yf squared equals v sub yi squared plus 2a y final.
If you did the first one first,
If we did the first one, I'm going to show you that we would, no, we could do that. It would be fine. We'd have to solve for time first, and then you could solve for peak height. You'd have to use two equations. Okay, so 0 squared equals v sub yi, or 12 squared, plus 2, negative 9.8, y final. And why did I leave off y initial here? It's 0. Yeah, you don't have to include that term. Okay. So negative 144 equals negative 19.6, y final. Okay. This was the simplest equation for us to use because we didn't have time. Okay. We could have solved for time to peak height and then used any of our equations, either the second or really the third, to solve for that. But that's kind of saving us a step here. Okay, do we agree with that 7.35 meters? Okay, now let's go about solving for time. And in this case, there's two ways we can solve for time. Okay, so I'm going to show you both ways. The first way would just be to use basically this symmetric projectile and look at it in halves. Okay, so if we look at the first half of our projectile to peak height, we could solve for the time it takes for it to reach this point right here. Okay, and it would be simple, right? Because what do we know about the velocity final at peak height? Our vertical velocity at peak height is 0. So we could use this equation, v sub yf equals v sub yi plus at, to solve for time at peak height. Okay, we could solve for the time it takes to get to peak height. Then what would we do to solve for total time? We multiply it by 2. Okay, does that kind of ring a bell from when we did our vertical things? We can solve for our time to peak height, then multiply it by 2. So that's a simple way to do it. So if we take 0 equals 12 plus negative 9.8 times time, okay, we can take negative 12 equals negative 9.8 t. But the important thing here is that we don't forget to multiply it by 2. Okay, so then we get a time of 2.44 seconds. Okay, so the important thing here is that we don't forget to multiply it by 2. There's a little trick though. We can only use this method when our projectile is completely symmetrical. Okay, when it starts and it lands at the same height. Yeah, okay, so this is our other method to solve for time, and it works regardless, but we've got a t and a t squared. Negative 4.9 t squared plus 12t plus 0 equals 0. What's this look like we probably need to do? Solve for the quadratic formula. Okay, if we have a squared, a regular, and then a no variable, we have to use the quadratic formula to solve for that. Okay, so this method works every time to solve for time, whether our y final and our y initial are the same or not, but it takes a little bit of extra work. So I'm not going to make you solve the quadratic right now, but you will have problems that you might have to solve for the quadratic. Okay, so if you need the quadratic formula, it is negative b plus or minus square root of b squared minus 4ac all over 2a. Okay, so that probably needs to go into your notes in case you need to use that. Okay. So this method of solving for time works every single time. It just takes a little bit of extra. All right, this problem is essentially the same as the last, okay? The steps to solve this one are almost exactly the same. So I want you to try to work through this one by yourself. Okay, so go ahead and start working through it by yourself. I'll be around if you have questions, but I want you to try and see how far you can get on your own. Okay? So this tells us a cannonball is fired at an angle of 31 degrees with an initial velocity of 89 meters per second from a height of 12 meters. Okay, so now our starting and our ending points aren't the same, so we can't use our peak height trick.
So does that mean our starting one's going to be 12 and our ending one's going to be 0?
You can choose to do it that way. I always choose my origin where my motion starts, so I'll make y final negative 12.
Okay.
Okay? So Caitlin's asking, could you make your initial height positive 12 and your final height 0? You could, okay, but I will always, always, always in class make my origin where my motion starts from, so my y initial is always 0. Okay, and then I'll make my y final negative 12. You can kind of do it either way, but just try to be consistent. So now instead of rolling off the cliff, we're launching it off the cliff. So we don't have a just straight rolling projectile anymore. We've got a launch. Okay. So first thing we have to do is break down that initial velocity vector. Okay, so now I've got my questions up here. What are components of initial velocity? We're going to break that down first. And then we want to find out how long until the cannonball hits the ground, which is solving for what variable? Time, good. And then what about how far did it travel horizontally? X, yep, X final. All right, so let's talk about this initial velocity vector first. Okay. V sub xi, am I going to use sine or cosine? I'm sorry, for v sub xi, we're going to use cosine. Okay, so 89 times cosine of 31. V sub yi, I'm going to take 89 times sine of 31. Okay, so a way that you can check yourself to make sure you've got this in the right order, you've got sine and cosine going the right way. If your angle's over 45 degrees, your vertical component should be bigger. If your angle's under 45 degrees, your horizontal component should be bigger. Okay, think about that. As I move through my angles here, okay, and let's think about a triangle being made under your little arm, okay, as I look at this, my horizontal component is bigger. As I start moving upward and increasing my angle to make the triangle, now my vertical component becomes bigger. Okay, so if you think about the right triangle that gets made, the lower my angle, the greater my horizontal component. The greater my angle is the greater vertical component. Does that make sense? Can we picture that? Or do you guys just like me doing this? All right, from this, we also know that x sub I is 0 and y sub I is 0. Okay. What equation can we use to solve for time? The second vertical one. Yes. Is equal negative 12. I'm sorry, I forgot to put that. Y final equals negative 12. Good, thank you. Okay, and that's because it lands 12 meters below where it started. So these equations take into account the fact that it's going up and then it's going to come back down. They do all of that work for us. Okay? So now to solve for time, we've got to use our second vertical equation, which means we have to use the quadratic. Okay, so gear yourself up here. Negative 12 equals 0 plus, we have a v sub yi now. In all of our rolling projectiles, we never had v sub yi, but now we do. Okay, so if I line this up in order of my quadratic formula needs, it's going to be negative 4.9 t squared plus 45.84 4t plus 12 would all equal 0. Okay, so I'm going to move my 12 to the other side, so I have it with my variables. Now my terms are a, b, and c. Okay, those are my terms for my quadratic formula. Okay. So as we go about solving this quadratic formula, doesn't the quadratic normally give you two answers? Yeah. So let's think about this. Could our answer for time ever be negative? Our time should never come out negative. So as you're solving the quadratic, you might be able to just skip one of those answers. Okay, so we're going to walk through this. I'm going to set it up, and then we're going to kind of look at where we can take that skip step to see maybe we can take a step out. Okay, so I'm going to solve the quadratic down below here. Negative b plus or minus the square root of b squared minus 4 times a c all over 2 times a. Do I have the numbers plugged in the right places, we think? Okay, so I'm going to go ahead and solve this whole term right here with our square root. Okay, so here's the part where I can kind of determine if I can take out a step or not. Okay, can I skip one of my answers? If I would use the plus 45.84 plus 48.3, would that give me a positive numerator or a negative numerator? It would give me a positive. And when I divide a positive number by a negative number, what's my outcome? A negative number. That means I don't even need to bother solving the plus. Okay, I don't even need to bother solving that. Okay, so I'm going to take negative 45.84 minus 48.34, and I'm going to divide that by negative 9.8, and I get a time equal to 9.6 seconds. Go ahead and solve for horizontal distance now on your own. $732.5 meters.